Yes, ma'am.
Good
Good
evening,
evening.
ma'am.
Good evening, ma'am.
Good
Good
evening.
evening.
Yeah. Prashant, am I audible?
Yes, ma'am. Yes, ma'am. You are audible. Ma'am,
Okay. So,
just
yeah, you can tell the instructions and then I can
yes,
start.
ma'am. Yes.
Thank you.
So, hello everyone. As we have also already sent one announcement via email. This session will be totally focused on the revising the key concepts of week 9 to week 12, which is important for end term. Okay, so please do not ask any general doubts or any operational related doubts. Those kind of issues we will take care of in the upcoming session, which is we have already scheduled on the Thursday 6 p.m. to 8 p.m. So I hope this is okay for everyone. Yes, ma'am. Now I think
Yeah.
we can start.
Thank you, Prashant. Yeah. Good evening, everyone. So, as Prashant informed, this session is just a revision session. I will not be taking any specific questions as to about an assignment problem or any other problem that has been a part of this course. If there are any questions regarding the context or the contents of this session, you may use the chat box or after every uh, topic, I'll give a couple of minutes or few minutes wherein we can discuss it. I hope that's okay with all of you. Okay. So what are we planning this session? This session is a revision session on random variables. Primarily, we are going to go back to the definition of a random variable, understand what is a random variable, introduce the notion of a probability mass function, a cumulative distribution function, the notion of expectation and variance of a random variable. Then we will go on to explain and review a few discrete distributions. In particular, we'll look at the Bernoulli, binomial, hypergeometric, and the Poisson distributions. And when we are looking at continuous distribution, we'll be looking mainly at the uniform and the exponential distribution. So this is the agenda for today. We will, the next 2 hours, we are going to try and revise these topics. Okay. So let's get started. If there are any questions, I will be checking the chat box. Uh, so Prashant, you can check the chat box, and if there is anything that
Uh,
is urgent, you can let me know.
sure, ma'am.
Is that
Sure,
fine?
ma'am.
Yeah.
Yeah, yes,
Thank
ma'am.
you. Yeah, that's a good thing. Right. So the first thing is, if you recall in probability, if you go back to the building blocks of probability, we started with the notion of a random experiment followed by a sample space, and the sample space was nothing but the set of all outcomes of this random experiment. Now, many a time when this random experiment is performed, you might not be interested in just the details of the result. What do I mean by this is, suppose I toss a coin, I'm getting head and tail. If I toss a coin twice, I'm going to have an outcome or a sample space which is HH, HT, TH, and TT. So this is my sample space. I might not be interested in knowing the outcome itself or the details of this outcome, but I might be interested in knowing how many heads are there in a particular outcome. So if I'm asking the question, the number of heads in a particular outcome, this outcome has two heads, this outcome has one head, this outcome has one head, and this outcome has no head. In other words, I'm interested in some numerical quantity determined by this result. So similarly, if I'm rolling a dice twice, what is the sample space? You can see the sample space on your screen. We have 36 possible outcomes. So I might not be interested in the outcome itself, but I might be interested in a function of these outcomes, which could be the sum of the outcomes. In that case, I can see that this outcome 1, 1 will give me the value 2, 1, 2 will give me the value 3. This will also give me the value 3. And I have a variable, that is, I can call it. So what I'm basically doing is, I'm not interested in the outcome, but I'm interested in some real valued function of these outcomes. So formally, we can define a random variable as a real valued function defined on the sample space. I repeat, when we are talking about a random variable, you go back to the definition of a random experiment, the sample space, and on this sample space, which is the set of all possible outcomes, I'm defining a real valued function. So you can see that what by valued function, I'm just mapping every outcome to a number. That is, I'm giving a quantity of interest. So this is why we are interested in random variables. Again, since it is mapping every outcome to a number, I can also assign the probabilities of this random variable. So let's go back to this example, which is rolling a dice twice. We have always seen that my sample space has 36 outcomes. The 36 outcomes are what you can see on your screen. So I might want to ask two questions. Out of these outcomes, how many outcomes result in a sum of 7? So if you look at it, this outcome 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1 result in a sum of 7. So I'm not interested in the outcome itself, but I'm interested in the sum of the outcome. So if I define a variable or a mapping to be the sum of the outcome, each of the outcomes in the sample space is mapped onto a value. So if you look at it, the outcome 1, 1, the outcome is 2. I'm mapping 1, 1 to 2, 1, 2 to 3, and so forth. You can see 6, 6 is mapped to 12. Every outcome is mapped to 12. Similarly, on the same sample space, I'm not interested in the outcome itself, but I'm interested in the lesser of the outcomes or the smaller of the outcomes. If the outcomes are same, I'm going to just take that value as the outcome. So if I'm looking at 1, 1, I know that the value is 1. 1, 2, 1 is smaller than 2. 2, 1, again 1 is smaller than 2. If you look at 2, 2, it is going to be 2. However, if I look at 3, 1, 3, 2, 3, 3, 2, 1, 3, 3, here it is 1, this is 2, this is a 2, this is a 1. So you can see that this, if I define X to be the sum of outcomes and Y to be the smaller of these two outcomes, here Y takes the value 1. In this outcome, Y takes the value 2. Here Y takes the value 1. In 3, 2, Y takes the value 2. So you can see that what you see on your screen is every outcome is mapped to a number. Any questions here? I'll pause for a minute if there are any questions. Is it clear?
Yes, ma'am.
Yeah, I'll proceed. Okay. So you can see that every outcome is passed to or it is mapped to a number. So I can now see that what are the values X are taking. If I look at the values X are taking, X takes the value 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. On the other hand, Y takes the value 1, 2, 3, 4, 5, and 6. So these are the values X are taking. So you can see that X takes value 2 up to 12. The relevant event I'm putting for every value X is taking, I have what is the relevant event. We have already defined what are the probabilities of these events. So I can define, once I know the relevant event which is mapped on to the value of the variable, I know that probability X is equal to 2 is the same as the probability that this event is going to happen, which I again know is 1 by 36. What is the probability of this? This is 2 by 36. The probability of this is 3 by 36. So this is nothing but probability X equal to 3. This is probability X equal to 4. So associated with every value this X is taking, I can assign probabilities, which we have done here. So probability X equal to 2 is 1 by 36. Probability X equal to 3 is 2 by 36. Probability X equal to 12 is again 1 by 36. Similarly, I can do the same exercise for y. What are y? Y takes the values 1, 2, 3, 4, 5, 6. I find out what are the relevant events, and you can see that probability y equal to 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It is 11 by 36. And I have the probability associated with y equal to 1 is 11 by 36. Probability associated with y equal to 2 is 9 by 36 and so forth. Probability y equal to 6 is 1 by 36. So a key takeaway that we have from whatever we have discussed so far is given a sample space, and so I start with a random experiment and a sample space. I am associating a real valued function with each outcome of this sample space. And I'm finding out what is the probability of that real value function, be it x or y, taking a particular value. Any questions still here? Is it clear?
Can you explain the last example, please?
See, here what we are doing is it, what is the value of the, how have I defined the y? I'm going back to my sample space, and the way I have defined my random variable is the value which is the smaller of the outcomes. If the outcomes are the same, I'm saying the value is going to be the same value. So what is the value y would take in the outcome 1, 1?
It would be 1.
1, 2?
It would still be 1.
Okay, so you can see that all these values are going to remain 1. Would you agree?
Yes, ma'am. Yeah.
Similarly, all of these are going to be 2.
Yes.
This would be 3. This would be 4. This would be 5. And this is 6. Would you agree?
Yes, ma'am.
So y takes the values 1, 2, 3, 4, 5, 6. Now I'm interested in knowing what is the probability with which y takes the value 1. Probability with which y takes the value 1 is same as this event happening. That is, these are my outcomes. How many outcomes are there? What is the probability of that event happening?
For y, it's 11.
It's 11, right? So probability y equal to 1 is 11 by 36. What is the probability of y equal to 2? How many events are there again? 1, 2,
5 by
3,
10.
4, 5,
10.
6, 7, 8, 9, right? 1, 2, 3, 4,
9.
5,
9,
9.
9, 9.
So 9 by 36. Probability y equal to 3?
7.
7 by
7 by
36.
36.
5 by 36. 3
5
by
by
36.
36, 3
And
by
1 by
36,
36.
1 by 36.
Till here, is it clear?
Yes, ma'am.
Yeah.
Yeah.
So I have just given you 2 examples. You could look at many more examples. You could define another random variable where I'm defining the z, for example, to be the maximum of the outcomes. Right? And I could define another variable, say z1, which is the difference of the outcomes. I'm just associating with every outcome a value. Do you understand? Is that clear?
Yes, ma'am. In
Right?
a sense, you are assigning a function to this subset of the sample
I'm
space you are talking
mapping.
about.
In other words, to understand what we are doing, we are mapping every outcome to a value. So
Okay,
that is what we have done. See, every outcome, all the 36 outcomes is mapped to a value. What is x? What is the function x doing? It is assigning every outcome to the sum of outcomes. What is y doing? It is assigning every outcome to the smaller of outcomes. Is that clear?
Yes, ma'am.
So I could have another value, say z, which is a larger of outcomes. Similarly, I'll say it is the same if it is equal to 1. So what is the value z will take for this outcome?
It would still be 1. The next would
1,
be
here
2.
it would be 2, this would be 3, and so forth. Is that clear? I can similarly find out what is probability z equal to 1, 2, 3, 4, 5, 6. Is that idea clear?
Yes, ma'am. It's fine.
Yes, ma'am.
Thank you.
Yeah. Any more questions? Okay. So now we can formally tell what is a discrete random variable and what is a continuous random variable. The first learning that you should have is that I am mapping the outcomes of the sample space to the real value function. We also saw when we defined the sample space, that sample space can be, you remember we talked about the time taken. When I talk about time taken, it is not discrete point, it is an interval. You all remember that? It is 0 to infinity. It could be anything between 0 and infinity. Right? So the sample space need not be just 1, 2, 3, 4 or something of that kind. It could be anything. So I'm mapping every outcome. So if the random variable can take countable number of possible values, it is called a discrete random variable. On the other hand, if it cannot be counted and it is infinitely divisible, I call it a continuous random variable. Just for ease of understanding, understand that a discrete random variable is one that has possible values, that I'm mapping every outcome onto discrete points in the real line. On the other hand, for a continuous random variable, I am mapping them onto an interval. I repeat, a discrete random variable is something where I'm mapping the points onto discrete points in the real number line. On the other hand, when I talk about a continuous random variable, the continuous random variable takes values in an interval. So when you talk about discrete random variable, it involves counting, whereas continuous random variable typically involve measuring. Is this clear? The distinction between a discrete and a continuous random variable?
Yes, ma'am.
Yes, ma'am.
Okay. So this is about the discrete and continuous random variable. Now the next thing is, how do I know? Suppose I'm given a question, how do I know whether it is a discrete random variable or a continuous random variable? So when I talk about number of people, do I count or do I measure number of people?
Count.
I count. Number of times a person takes a particular test. You see, all the examples, number of times, number of accidents, number of spelling mistakes, you don't measure them, you rather count them. Agreed? On the other hand, do you count the temperature of a person or do you measure the temperature of a person?
Measure.
Similarly, height and weight, do you count or do you measure?
Measure.
Speed of a vehicle, do you
Measure.
count or do you measure?
Measure.
Measure.
Do you measure time or do you count time? I'm not telling number of hours taken. I'm taking the total time taken. Do you measure it or do you count it? When I'm talking about number of hours, I'm counting the number of hours. But when I'm just looking at the total amount of time taken,
Measure.
you measure it. Okay. So a good way to understand whether the variable in context is a discrete or a continuous variable is for you to look back and see that am I involving a counting or am I involving a measuring? Is this clear?
Yes,
Ma'am.
Okay. So the next context is now, okay, I have defined a random variable. Now let's focus on a discrete random variable for some time. When I tell about a discrete variable, I have x, which can take x1, x2. These are discrete values. If it is finitely number, I stop with xn. If it is infinitely many, it will be x1, x2, x3. These are all, and I have infinitely many values, but they are countable. Okay. And I know that, for example, in that, when I'm looking at the sum of outcomes, x took the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. These were the discrete, finitely countable values x took. And associated with every value x took, I had a probability. So representing that in a tabular form where x takes values x1, x2 up to xn, with the probability of x taking to xi, this is what probability x equal to xi is called the probability mass function of the random variable. I repeat, probability x takes a particular value xi and the distribution of that is called the probability mass function, okay, of that random variable. Now, this probability mass function has certain properties. What are the properties? A, because it's a probability, 0 is less than probability x is equal to xi is less than or equal to 1. It is a probability measure. And over all values x takes, the summation of probability x equal to xi should be equal to 1. So let's go back to our example and check whether it was a probability mass function. What is the sum of all probabilities here? You can fill it up here. So what would probability x equal to 6 be? Any idea? I missed out x equal to 6, 7, and 8. What would probability x equal to 6 be? What is probability x equal to 6? It is 5 by 36. What is probability x equal to 7?
6 by
X equal to
36.
7. It would be 6 by 36. All the diagonal values, right? And probability x equal to 8?
5 by 36.
It's again 5 by 36. And what do you think would be the sum of all these values? 1 plus 2 plus 3 plus 4 plus 5. What is 1 plus 2 plus 3 plus 4 plus 5? Plus 6, again plus 5 plus 4 plus 3 plus 2. You know, all of this add up to 36. So I get 36 by 36, which is 1. Similarly, what is the sum of these values? 11 plus 9, 20. 20 plus 7, 27. 32, 35, 36, 36 by 36, I get, they add up to 1. Is it clear? So one of the problems that you all would encounter is, we'll give you some function and ask you to verify whether it is a probability mass function. So what are the two things that you do when you are asked to verify whether it is a probability mass function? You need to check. For example, I could have something of this kind where x takes the value a, b, c, and I have a 3 by 4, I have a 2 by 4, and I have a minus 1 by 4. Okay? Is this a probability mass function?
No, ma'am.
No, ma'am.
No,
It is not a probability
negative.
mass function because this is minus 1 by 4. Even though it is 5 minus 1 by 4, even though it adds up to 1, it is not a probability mass function. Is that clear?
Yes, ma'am.
Yes, ma'am.
So this is about the probability mass function. And what is the this one? It should be greater or equal to 0, and the sum should be equal to 1. Now the next thing is, how do I graph this probability mass function? Now if I look at the value, I know x takes discrete values, so I can put those discrete values on the x-axis, and on the y-axis I can just plot the probability x equal to x. So you can see here the value x takes are 1, 2, 3, and 4. Probability x equal to 1 is 0.4. Probability x, first of all, is this a probability mass function? It is, because it is positive. And what is it? What is 0.4 plus 0.3? It's 0.7 plus 0.2 is 0.91. It is a probability mass function. And you can see that the height of the bars represent the probability x equal to xi. Now, this will tell us, help us understand whether the distribution of the random variable is symmetric, or is it skewed, or is it flat, or is it uniform, and everything. So what you see on your screens is a positively skewed distribution. Now, on the other hand, what can you say about this distribution? You can see it is a mirror image of the earlier one. So this is a negatively skewed distribution. So how do you think this would be? 0.25, 0.25, 0.25, and 0.25. X1. First of all, is it a probability mass function?
Yes, ma'am.
X takes
Yes,
value 1, 2, 3, 4. So what would be the graph?
That would be
Symmetric.
uniform
Uniform
distribution.
distribution.
It would be uniform. So I'll have everything 0.25, 0.25. I'll have a 0.25 and a 0.25. And you'll see that this blue, this one is going to be the probability mass function of that. You see all the bars of the same height. Is that clear? Yeah. So the
Yes,
next
ma'am.
concept is that of a cumulative distribution function. The probability mass function gave me the distribution, or it told me what are the values x takes and what is the probability with which x takes that particular value. Now, cumulative distribution function is a function. See, all of them are actually functions. So the minute I tell about function, I need to have from where am I mapping it. So cumulative distribution function is basically a function which maps every point on the real line to this 0, 1. Why is it 0, 1? Because I'm defining this function f of a for every real point a as probability x is less than or equal to a. Okay. So you can see that if x is a random variable whose positive values are x1, x2, such that x1 is less than, x2 is less than x3, then what is the shape of the cumulative distribution function? So let's look at our example. In our example, I had x taking the value 1, 2, 3, 4. 1 is less than 2, is less than 3, is less than 4. What is probability x is less than 1? Because I know that for all values which are other than 1, 2, 3, 4, what is probability x equal to something? It is 0. Would you all agree with me? So probability x is less than 1 is going to be 0 for all the x's which are less than 1.
Yes, ma'am.
Right? So when I'm talking about probability x is less than 1, I'm going to all, suppose I have 1 here, 2 here, 3 here, and 4 here. Okay, till this point, my f of x is going to be 0. Would you all agree with me?
Yes, ma'am.
At x equal to 1, what is happening to probability x equal to 1? It becomes 0.1. I'm having a jump here. Right? What is probability x is less than or equal to 1.1?
0.
Less than or equal to? It will be probability x is equal to 1, right? Because probability x is less than or equal to 1.1. I have probability x is equal to 1 there. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Right. What about 1.2?
Point
It
one.
will also be 0.1. 1.3 will be 0.1. 1.9 will be 0.1. 1.99 will be 0.1. So it is going to remain to be 0.1 till the minute it hits 2. At 2, what is happening?
0.
I'm having another jump, right? And what is that jump? It would be 0.2 plus 0.1, which is going to be 0.3. It will remain 0.3 till it hits 3. Do you get the idea? Cumulative is I'm accumulating the probabilities. So look at this problem. What is probability x is less than or equal to 1? Less than 1, sorry, strictly less than 1.
0.
0.
0, 0.
At x equal to 1, I'm getting this one. So between 1 and 2, it is going to be 1 by 4. Agreed? Right? Between 2 and 3, it would be 1 by 4 plus 1 by 2, which is 3 by 4. Right? At 3, again, I'm getting a jump, and it is going to be 3 by 4 plus 1 by 8, which is 6 by 8 plus 1 by 8, which is 7 by 8. And then it is going to remain 1. So you can see that if I have a discrete random variable, I'll have the cumulative distribution function. So this is 0. Up to 1, it was 0. All of them were 0. At 1, it is having a jump. At 2, it is having a jump. At 3, it is having a jump. And after this, it is going to remain at 1. Would you all agree with me? Because it is a probability x is less than, it can never go beyond 1. Do you all agree with it? Because it's a probability, it's a cumulative probability. Probability x is less than or equal to a. I know that this f of a is between 0 and 1. And the shape of the cumulative distribution function for a discrete random variable is a step function as displayed on your screen. Any questions still here?
Ma'am, can you repeat the last point?
Till here, is it clear that I'm having x is less than 0? It would be till it is 1, it is going to remain at 0. Would you all agree? At x
Yes,
equal to 1, it is going to jump to 0.2. It will remain at 0.2 till it is at 2. What was x equal to 2? X equal to 2 is 0.5. So at x, sorry, this was 0.25. Okay. At x equal to 2, it is 0.25 plus 0.5, which is a 0.75. So you can see that it is jumping to 0.75. It will remain at 0.75 till x equal to 3. X equal to 3 is 1 by 8. So I add that, I'm going at 7 by 8. I continue to be here. And at x equal to 4, it is again 1 by 8. I become 8 by 8. And beyond this, it's always going to be 1. Is that clear? Any questions here?
No, ma'am. Clear.
Is it clear? So a cumulative distribution function is a discontinuous function. That's why these are the discontinuities. It is not joining. These are discontinuities. So how does that graph actually look? It looks this way because there are discontinuities. It looks like a ladder. It's called a step graph. Is that clear? Yeah?
Yes, ma'am.
It is discontinuous graph. So now the idea is I have introduced the notion of a random variable. We have seen what is the probability mass function of a random variable and what is the cumulative distribution function of a random variable. There are two very important concepts that are associated with a random variable. One is a concept of an expectation and one is a concept of a variance. Now, what is expectation of a random variable? Now, again, we all need to understand that this random variable itself is a construct in an uncertainty. That is in a probability. It is an uncertain. Probability itself is a tool to understand uncertainty. So the word expectation is defined or it is considered as something as a long run average. For example, if I continue to toss a coin, say 10,000 times, then how many heads can I expect to have? Do you get the idea? Okay. If I'm continuing to toss a coin some 10,000 times, then how many of these would be, how many heads would I expect to have? Similarly, if I am rolling a die, say 10,000 times, then in how many cases will I get a sum greater or equal to 5? I can ask questions of this kind, and you see that the way we are asking the question is, what is the long run average? That is what expectation can be viewed as. How can I mathematically define expectation? The mathematical definition of expectation is expectation of x is xi into probability x equal to xi. Again, going back to our example, what were the values x takes? X takes finitely many values. So the expectation is xi into probability x equal to xi, summation over I going from 1 to 4, which would be 1 into 1 by 4, plus 2 into 1 by 2, plus 3 into 1 by 8, plus 4 into 1 by 8. This is what is called the expectation of a random variable. Suppose x takes only two values, 0 and 1, with probability half and half. What is the expectation of x? It is going to be 0 into half plus 1 into half. Would you all agree? Which is equal to half.
Yes.
Right? So this doesn't mean that if I am going, suppose I'm mapping a tail to 0 and a head to 1. This doesn't mean that if you are going to toss a coin 10,000 times, then sometime you might get half as the value. That does not mean. Expectation of x is not, that does not mean that. It says that the long run average of the values x is taking would be half. Is that clear? The notion of long run average. Yeah, expectation can be considered as a long run average. Now let's look at the expectation. I'm taking first random variable, x is taking the value 0 with probability 1. So what is the expectation of x here?
0.
0. Now I'm having y, which is taking two values, minus 2 and 2 with probability half and half. What is expectation of y?
0 again.
0. I'm having z, which is taking the value minus 20 and 20 again with probability half and half. What is the expectation of z? It's again 0. So you can see that the expectation of x is equal to y is equal to z, which is equal to 0. But however, the spread or dispersion of these variables are very, very different. You see that x has no dispersion. It is taking the probability 0 with probability, it is taking only one value. Y is taking minus 2 and plus 2, and z is taking minus 20 and plus 20. So that is where we introduce the notion of a variance of a random variable. And as you know, in numerical or when we did numerical measures, we defined the variance as I going from 1 to n, xi minus mu whole square 1 by n. If it is, again, whether it is n or n minus 1, I will just leave it at 1 by n here. So the similar analogous definition is expectation of x minus mu whole square, where mu is the mean or the expected value. Now, one way to also compute the expectation of x is looking at expectation of x square minus expectation of x whole square, which is expectation of x square minus mu square. This is a very nice computational formula to find out the expectation. Okay, let me check the chats. Okay. Concept is okay. Will you teach questions from practice assignment? No, I'm not going to teach questions from practice assignment. I'm only going to teach the concepts. Okay. Right.
Ma'am, can you just repeat the expectation again, ma'am?
The notion of expectation.
Yes, ma'am.
Yeah. See, the notion of expectation is, suppose I'm having X, I am tossing a coin once. Okay. What are the outcomes of this experiment?
Heads and
Head and tail. Let me map a head as 1 and tail as 0. No sanctity about it. I can do the other way around also. What is the probability X equal to I? This is a half and this is a half if I have a fair coin. Till here, is it right?
yes, ma'am.
So if I'm applying the mathematical definition of expectation, what would this be? This would be 1 into half plus 0 into half, which is a half. Is that clear? Right? So this doesn't mean that if you're tossing a coin 10,000 times, you'll get a coin where it is neither head. That's not what it means, because X is taking only values 1 or 0. Right? The way you can understand expectation is, if I toss a coin sufficiently large number of times, then the average of the value 1 and 0 is half. So that's why expectation can be observed or considered as a long run average. Is this clear?
Yes, ma'am.
Yeah.
Yes, ma'am.
So it need not take, expectation need not be a value that the random variable is taking. So similarly, I have introduced the notion of a variance, which is expectation of the deviation whole square. What is x minus mu? X minus mu is nothing but the deviation of the random variable from its expectation. The expectation of the square deviation is what the variance is. And the computational formula is expectation x square minus mu square. You can refer to the lectures. We have given a detailed thing about how we come at this computational formula. So whenever I'm talking about expectation, so you can see even here I have given what is the computational formula, which is nothing but expectation of x square minus mu square. So let's go back to this value. Let's look at some specific random variables. Okay. The first discrete random variable is the simplest of the kind, is what we call a Bernoulli random variable, because a Bernoulli experiment is an experiment which has only two outcomes, which is a success and a failure. Okay. One word of caution here is, it does not mean that the outcomes are only two. The way I can define, for example, if I roll a die and I define an odd number to be a success and an even number to be a failure, I have a Bernoulli experiment. Is that clear? I'm mapping. So what would be it? I'm mapping all the odd numbers to a success and mapping all the even numbers to a failure. So I can map the failure to 0 and success to 1. I know if the probability of my failure is success is p, then the failure is 1 minus p, because these are the only values that I'm allowing the Bernoulli random variable to take. Is it clear? It is taking the value which is, it has only two outcomes. I'm mapping these two outcomes to two values. I'm saying probability x equal to 0 is 1 minus p and x equal to 1 is p. Till here, is it clear?
Yes, ma'am.
Yeah. Now, what is the expectation of the random variable? Expectation is 0 into 1 minus p plus 1 into p, which is p. Now, what is x? What if x takes the value 0 and 1? What is the value x square would take?
0 and 1.
0 and 1.
0 and
What is
1.
the probability x square equal to 0? That is 1 by 2, 1 by 1 minus p. Right? What is the probability x square equal to 1? That is p. So what is your expectation of x square? That will also be a 0 into 1 minus p plus 1 into p, which is a p. Now go back to the computation formula of variance of x. It was expectation of x square minus expectation of x whole square. What is expectation of x square? I just have it here.
P.
Expectation of x square.
P.
It is p. Expectation of x is p. So I have a p minus p square, which is p into 1 minus p. So I know that if x is a Bernoulli random variable with parameter p, the expectation of that random variable is p, and the variance of the random variable is p into 1 minus p. Is this clear?
Yes,
So
ma'am.
given a random variable, just like whenever you're talking about yourself, you have your address, name, Aadhaar number, phone number, and everything. So given a random variable, we specify the parameter of the random variable. We specify the probability mass function. We also give the expected value and the variance of the random variable. Is this clear?
Yes, ma'am.
Yes,
Okay.
ma'am.
Now let's look at the next random variable, which is called, pardon?
Madam, any one example for the
Tossing a
Bernoulli
coin.
random? Okay.
We'll look at different. Okay, tossing a coin, it's a Bernoulli random variable. Rolling a die where odd number is success, even number is failure. What is P there? What is the probability x equal to 0 there?
Yeah, half.
If odd number is a success, and I'm mapping success to 1, even number is failure. What is probability x equal to 0? What is the probability of getting an even number when you're rolling a die?
Half.
Yeah, when you're rolling a die, a fair die, what is the probability of getting an even number?
Half.
What is my sample space when I roll a die? What are the outcomes? 1, 2, 3, 4, 5, 6.
1 to 6.
What is the chance of getting an even number?
2, 4, 6.
What
That
is
is
the chance
3
of getting an
divided
even
by
number?
3 by 6. 3 by 6.
1 by
3
2,
by
3 by
6.
6, which is 1 by 2. Chance of getting an odd number? 1 by 2, right? So I can define, I'll have a lot of situations where I can define only 2 outcomes, which is a success and a failure. Is that clear?
Yes, ma'am. It's clear.
Yeah.
Thank you.
Now the next thing is, again, go back to rolling a die. What is my random, what is my this one? It is 1, 2, 3, 4, 5, 6. If a random experiment is just noting what is the outcome of the experiment, what are the values my random variable is taking in that case? I'm just noting what is the outcome on the rolling of the die. What are the values the outcome the random variable is taking?
1 by 6 for everyone.
If I see a 1, it will be 1. If I see a 2, it is 2. What are the values that
It's 1 by 6 for everyone.
yeah?
It's 1 to 6, ma'am.
Yeah, 1, 2, 3, 4, 5, 6. What is the probability with x takes the value I? What is the probability with which I can get a 1? It's a fair die.
1
1
by
by
6.
6.
1 by 6.
1 by 6.
1 by 6. 2,
1 by
Same.
6.
1 by 6. 3, again 1 by 6. 4, 1 by 6. 5, 1 by 6. 6, 1 by 6. So here I have a random variable, which is, hello? Hello?
Yes, ma'am.
Ma'am.
There was some talking happening. Okay, anyway. Can I proceed?
Yes, ma'am.
Yes, ma'am.
So you can see that x takes the value 1, 2, 3, 4, 5, 6 with probability 1 by 6, 1 by 6 up to 1 by 6. Till here, is it clear? Right?
Yes, ma'am.
So what is the expectation of this random variable? It would be 1 into 1 by 6 plus 2 into 1 by 6 so far. So it would be 1 by 6 into 1 plus 2 plus 3 plus 4 plus 5 plus 6. Would you all agree? That's the
Yes, ma'am.
expectation of the random variable. What
Yes,
is 1
ma'am.
plus 2 plus 3 plus 4 plus 5 plus 6?
N into
It's
n
a
plus 1
sum
by
of
2.
integers.
It is
It's
20.
a sum of odd n integers.
Yeah, so what would that be? 21, right?
21.
Right. Yeah,
Yes, ma'am.
is that right?
Yes, ma'am.
Yes, ma'am.
1 plus 2, so 5, 10, 15, 21, right? 21 by 6, which is nothing but 7 by 2. Yeah. But what does this mean? This means that if I sufficiently throw a die for many times, then the expected value of the long run average of, see, x takes value 1, 2, 3, 4, 5, 6. The long run average is going to be 3.5, which is 7 by 2. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah. Now, what are the
Yes,
values
ma'am.
x square would take? If x takes the value 1, 2, 3, 4, 5, 6, what are the value x square would take?
1 plus 4 plus 9 plus 16 plus 25 plus 36.
4, 9,
What are the values x square
16,
would take?
25, 36.
If x takes the value 1, what is the value x square would take? If
1
x equal to 1, what is the value x square? 1. If x takes the value 2, what is the value x square would take?
4.
4.
4.
4, 9,
25 and
16,
25.
25,
20,
and 36.
30.
What is the probability with which x square is equal to 1? That would be 1 by 6. This will be 1 by 6. This is again 1 by 6. 1 by 6. 1 by 6. 1 by 6. Is that clear? So what is expectation of x square? It is 1 into 1 by 6 plus 4 into Hello, am I audible?
Yes, ma'am.
Yes.
Yeah, now
I
it is
think
okay.
I think my connection dropped for a minute. Let me share my screen. Is my screen visible?
No, ma'am.
Is
No,
the
ma'am.
is the
Yeah,
PDF
now
visible,
it's
please?
now
Yeah?
it's
Yes,
visible.
ma'am.
Okay.
Yes,
Right.
ma'am.
So I was telling you were you all there when I was talking about x square? Values that x square would take and the probability with which it takes these values?
Yes, ma'am. Yes.
Yeah. So I can define expectation of x square to be 1 into 1 by 6 plus 2 square into 1 by 6 plus 3 square into 1 by 6. So what is 1 square plus 2 square plus 3 square plus 6 square? So just I had 1 plus 2 plus 3. I'll have expectation of x square equal to 1 by 6 into 1 square plus 2 square plus 3 square up to 6 square. Would you all agree with it? I know
Yes,
what is the sum of squares, right? What would be the sum of squares?
Yes, ma'am.
It's nothing but n into 2n plus 1. That is how I'll get it, right? Is it clear?
Yes, ma'am.
Right. So you can see that if I have a random variable which takes the value 1, 2 up to n, in this case n was 6, with the same probability, that is a discrete uniform distribution. That is, it is taking these discrete values with the same probability, then expectation of that random variable is n plus 1 by 2. In my rolling a die case, n was 6, so I had a 7 by 2. And variance of x is n square minus 1 by 2. So in here, I'll have 35 by 12 because n is 6, n square is 36. I'll get 35 by 12. Is this clear?
Yes,
For
ma'am.
a discrete
Yes, ma'am.
random variable?
Yes, ma'am.
Now, let's go and spend some time in understanding what is a Bernoulli distribution, binomial distribution. Before I go to binomial distribution, we need to understand what we mean by independent and identically distributed trials. I repeat, independent and identically distributed trials. So let me ask you this question. Suppose I'm tossing a coin one time. Okay, first time. What is the chance of me getting a head?
Half.
Okay,
1 by 2.
and 1 by 2. Now I'm tossing the same coin the second time. What is the chance of me getting a head then?
Half.
Half 1 by 2.
Does
One
that
by two.
depend on whether I got a head in my first toss or not?
No.
It is an
That
independent
is,
event.
it is independent. It's not only independent, it is identical also, right? If the probability of getting a head is the same. So another thing is, suppose I have 4 red balls and 4 blue balls, or 4 red balls and 4 blue balls. I'm picking up one ball at random, noting the color and keeping it back. Okay, what are the outcomes of this experiment?
Eight.
What are the outcomes? I'll describe the experiment. I'm just picking up a ball at random, noting down the color and replacing that ball. They're identical red balls and identical blue balls. What are the outcomes of this experiment?
Ma'am,
Two out.
any of two, ma'am. Red
Two out.
It is either a red ball or a blue ball. Would you all agree? What is the
Yes.
chance with which I get a red ball?
1
4
by
by 8.
1 by
1/8.
By 2.
1/8.
Chance with which I get a blue ball?
1 by
Again,
8.
1 by
1 by 2. Okay. So first I pick up a ball, I keep it. What is the chance with which I'm repeating this experiment? First time I do. Okay, first time, first trial. What is the chance with which I get a red ball?
1 by 2.
1 by
1
2.
by 2.
A blue
By
ball?
1
1
by
by
2.
2.
1 by 2.
Second trial. What is the chance with which I get a red ball? It
1
would
by
be 1 by
1
2.
by 2.
Still 1 by 2.
And the chance with, because I'm replacing it, the chance with which I'm getting a red ball in my second trial is independent of whether it was a red or a blue in the first trial.
Yes.
Great.
Yes,
This is
ma'am.
also 1 by 2. So you can see that these are independent and identically distributed Bernoulli trials because I have only 2 outcomes. I can tell the red is a success and blue is a failure. Till here, is it clear?
Yes, ma'am.
Ma'am,
Now I'm doing, yeah?
can you repeat the identical that one alone, ma'am?
Yeah, see, what is the chance with which I'm getting a red in the second one? First of all, are you convinced that the second trial is independent of the first one? The
Yes.
chance, right? Now it's the same probability, right? The identical. Let me explain another example, and then you'll get a thing. Now, in the first trial, the second way I'm doing the experiment. In the first trial, I'm picking up a ball. Okay, I'm keeping that ball aside. But what is the chance in the first trial I'm going to get a red?
1 by 2.
I can get either a red or a blue with probability 1 by 2, 1 by 2, right? In the second trial, I'm not replacing this red ball again. So if it was a red in the first trial, so what is it? It could be a red or it could be a blue, right? What is the chance
Yes,
with
ma'am.
which it's a red? It is 1 by 2 or it's 4 by 8 and this is 4 by 8. If it is a red, okay, at the second trial, again I could have a red or a blue. Do you all agree?
Yes, ma'am.
But what is the chance with which I pick up a red now?
3 by 7.
It would be 3 by 7 and this would be 4 by 7. So you can see that the second trial is dependent on whether it was a red in the, what is the chance with which it's going to be a red here if I pick up a blue?
4 by 7.
4 by 7. So you can see that the
7.
second trial is not independent of the first trial and they are not identically distributed also, right? This would be 3 by 7. If it were a red or 4 by 7, if it's a red, this is 4 by 7 and 3 by 7. Is that clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yeah. So that is the idea of independent and identically distributed trials. Now, a collection of these this distribution share a common probability distribution. So when I look at a Bernoulli trial, okay, and I now defining a binomial random variable. A binomial random variable assumes that I have n independent Bernoulli trials, each of which has, and the Bernoulli trial, we have already said it has a success or a failure. Success is with probability P, failure is with probability 1 minus P. So the first trial, what would be the probability of success? If this is a head and tail, probability of success is P, probability of failure is 1 minus P. Second trial, again P, 1 minus P. Third trial again P, 1 minus P. Nth trial is again P and 1 minus P. Is this clear?
Yes, ma'am.
So what is the X? What is the Bernoulli random variable counting? It is counting. Again, remember, a discrete random variable is counting the number. So it is counting the number of successes in n trial. So let me look at a simple example. I'm tossing a coin twice. So HH, HT, TH, and TT. Head is a success, tail is a failure. What is the probability with which what is my P here? What is the probability with which I get a head? What is P? Probability of getting a head.
3 by 4.
3 by 4.
Head.
1 by 2.
It's 1 by 2, right? In one
1
trial,
by 2.
probability of getting a head is 1 by 2. This is also 1 by 2, right? Right. Now, I am having two independent trials. When I'm tossing a coin twice, I'm having two independent trials. Okay. I am counting the total number of heads in two independent trials. So what are the values this X can take?
1 by 4.
Values X can take.
0,
How many
1,
heads do I have in this outcome?
0, 1, 2.
This is
1
1
and
and this is, so this takes the value 0, 1 and 2. The number of heads in the outcome, right? Number of heads in two trials. Number of heads in two trials, two independent trials. What is the probability with which X takes the value 0? Probability with which 1 by
1 by
4
4.
takes the value
1
1.
by 4.
2 by 4. This is 1 by 4. Is this
1
clear?
by 4.
Yes,
Okay.
ma'am.
Yes,
Now,
Yes, madam.
I'll give you 1 minute. Do it for 3 trials. N equal to 3. I'll give you a minute. N equal to 3. Please do it. What are the values X will take? Again, I'm counting the number of heads. First of all, is it a Bernoulli
0, 1,
experiment?
2, and 3, mom.
0, 1, 2, and 3. Right?
Yes, mom.
What is the probability with which X equal to 0 again?
1 by 8.
1 by 8, 3 by 8,
X
1
equal
by
to
8.
3.
1 by 8.
It is again 1
1
by
by
8. This is a 3 by 8.
3 by
3
8.
by
This is
8.
3 by
3
8.
by 8.
Is this clear now? Yeah.
Yes, ma'am.
So in general,
Yes, ma'am.
and I
Clear.
know that it is a binomial experiment because the probability of me getting a head in the first trial is identical to the probability of me getting a head in the second trial to identical to the getting a head in the third trial. Right? And they are independent. Whether I'm getting a head in the second trial is independent of whether I got a head in the first, which is independent of whether I got a head in the second. Is that clear? Right? So in general, if I have n independent Bernoulli trials and X is the number of success, if I have all successes, we know that if I have independent events, what can I say about probability of A intersection B?
Probability of A into probability of
B, right? So probability of getting a success in all the n is probability of success in first into probability of success in 2 into probability of success in n, which is P into P into P, which is P to the power of n. Is that clear?
Yes, ma'am.
Yes, ma'am.
Now, what would be the, suppose this is the outcome, SSS, and only I have n success, n minus 1 successes and 1 failure. What would the probability of this be? How
P
many
the
times
power
will I?
n minus 1
P to the power of n minus 1 into 1 minus
into
P.
1 minus P.
right.
Now, this failure can be last, or it could be the n minus 1, or it could be the first one. Would you all agree? Right? So, how many P to the power of n minus 1 into 1 minus P will I have? The probability of n minus 1 successes. How many will I have? I can have a n minus 1 success this way, or this way, or this way. So what is the probability of me getting, what is the probability of me getting all successes? It is p to the power of n. All of you agree with this?
Yes, ma'am.
Now the next one is I'm asking what is the probability of me getting n minus 1 successes? So that could be either a last failure or the last but one failure or the last but two failure or the first failure. Agreed?
Yeah.
Yes, ma'am.
What is the probability of the last failure? It is p to the power of n minus 1 into 1 minus p.
1
What
minus.
would this be? This would be p to the power of n minus 2, 1 minus p into p, which is again p to the power of n minus 1 into 1 minus p. Would you all agree?
Yes, ma'am.
Yes, ma'am.
Again, the next one would p into p, 1 minus p into p into p. Again, which is p to the power of n minus 1 into 1 minus p. So what is the total probability of n minus 1 successes? That would be p to the power of n minus 1 into 1 minus p. How many times? How many times will I add it?
N times.
N times.
Right? Now let's look at two failures. In two failures, what would be this probability? Of two failures, how many successes will I have? N
P to the
minus 2
power n
successes.
minus 2.
So
P to
it
the
will
power
be
n
p to the power of n minus 2 into 1 minus p. But how many times will I have it? How many times will that occur?
N times.
n
Will it be
times.
n times? No. I'm
The two.
choosing
N.
n choose 2, right? Why is it n choose 2? Because I have two failures that can occur in any one of the n places. How many ways can I choose two failures from n places? Again, you're counting, right? I have two failures. How many successes I have? I have n minus 2
N
successes.
minus 2.
I have n places. I need only two failures. How many ways can I put these two failures in n successes, n points? N choose 2, right? Is it clear? So in general, tell me what would probability x equal to IB? That is I successes. What would that be? If or
N,
I failures, it would be
N choose I, P to
I
the power N minus I, 1 minus
into
P.
1 minus p to the power of I, right?
Yeah.
Is that clear? P to the power of I. If it is failures, it would be p to the power of n minus I, or it is p to the power of I into 1 minus p to the power n minus I. So you can see that the probability of I successes in n trials is given as n choose I into p to the power of I into 1 minus p to the power of n minus I. Is the idea clear as to how we have got this? This is the probability mass function, and I tell that x is a binomial random variable with parameter n and p. What is n? It is the total number of independent trials, and p is the probability of success in each trial. Then I know that the probability mass function is n choose I into p to the power of I into 1 minus p to the power of n minus I. And what are the values this I can take? It can take values 0, 1, 2, up to n. Is this clear? Any questions?
No, ma'am.
Is it clear,
No,
please?
ma'am.
Okay.
Yes, ma'am. Clear.
Now, the next thing is, so this is how we define a binomial random variable. Expectation of a binomial random variable. So even before we go to the expectation of a binomial random variable, I'll just show you what is the graph or the PMF of a binomial random variable. You can see for n equal to 4 and 0.3, this is how the binomial random variable would look. N equal to 4 and 0.5, you see that it is symmetric. Okay, same n, but 0.3, it is this way. If it is 0.5, it is this way. And 0.7 or 0.8, you see, you'll have a left skewed or right skewed. If it is P is high, it is a left skewed. P is low, it is a right skewed. Now, what do you notice? If n equal to 40 and P equal to 0.3, what is happening to this? You can see that the entire thing is shifted to the left, right? So if n equal to 40 and P equal to 0.5, what would you expect? You'd expect that PMF to be of this kind. and n equal to 40 and p equal to 0.8, you see a PMF of this type. Okay. So what is the expectation of a binomial random variable? I know that x, that is a binomial random variable, can be written as the sum of n independent and identically distributed Bernoulli random variables. What was the expectation of a Bernoulli random variable with parameter p? What was expectation of xi? This was p. Agreed?
Yes.
Right? So if expectation, if I have two random variables, what is expectation of x plus y? It is expectation of x plus expectation of y. This is the property of expectation. The expectation of a sum is sum of expectation. Is that clear? Right?
Yes, ma'am.
So what would expectation of x be here? This would be expectation of x1 plus expectation of x2 up to expectation of xn. What is expectation of x1? It is p plus p plus p. How many times am I adding this p?
And
n times.
So
N
expectation of a binomial random variable is n into p. Is it clear?
Yes, ma'am.
Yes,
Right?
Yes, ma'am.
Right? So the expectation of a binomial random variable is n into p. So similarly, what is the variance? Suppose I have x and y are two random variables. They are independent. Then variance of x plus y is variance of x plus variance of y. Okay? They should be independent. So here my x1, x2, xn are independent. So what would variance of x be? It would be variance of x1 plus variance of x2 plus variance of xn. But what is the variance of a Bernoulli random variable? We have already seen that is p into 1 minus p. Agreed?
yes, ma'am.
Yes, ma'am.
So this would be p into 1 minus p plus p into 1 minus p. I'm adding it n times. So what will be the variance of a Bernoulli random variable?
NP into 1
NP
minus
n
p.
into
1 minus
p into 1 minus p. So you can see that the expectation is n into p and variance is np into 1 minus p. Okay? Till here, is it clear?
Yes, ma'am.
Right.
Yes, ma'am.
So we saw that
Yes, ma'am.
when I have the probability of success in an n trial are independent and identical, I could have a Bernoulli. I have independent and identically distributed Bernoulli trials, binomial distribution worked well. But now suppose I have this kind. I have 4 white balls and 3 black balls. And if I have a black, what is the probability with which the first trial I take a black ball?
3/7.
I'm not replacing it. So if it's a black ball in the second trial, how many balls are left? I'll have 4 white and 2 black balls. Is that right? Because I'm not replacing. If I get a black ball, I get 4 white and 2 black. If it is a white ball, I get 3 white and 3 black. So now what is the probability of drawing a black ball from the in the second trial?
1/3.
1
Okay,
by 3.
white ball, it's 2 by 3. Agreed. This is not identical to this. So the probability of drawing a black ball in the second trial is not the same as probability of drawing a black ball in the first trial. Would you agree? It is not identical and it's not independent either. So I cannot get a Bernoulli binomial distribution because when I wanted to talk about a binomial distribution, the IID was very important. Is this clear?
Yes.
Yes,
Yes,
ma'am.
ma'am.
Yeah. Right. So we will introduce what is hypergeometric distribution. When you're talking about hypergeometric, again, I might be able to divide the entire thing into 2 subsets. So black ball or white ball. It has changing probability of success with each experiment. So here you can see that in this example, I have changing probability of experiment. I'm drawing the sample without replacement. I'm not replacing it B. So what is a hypergeometric random variable? I again have a fixed number of trials. Again, I had 2 trials here. But the probability of success is not the same from trial to trial. In the binomial, I had a fixed number of trials and the probability of success was same from trial to trial and it was independent. Is this clear? The difference between binomial trial and hypergeometric distribution?
Yes, ma'am.
The probability
Yes,
is
ma'am.
not the same. So what is the hypergeometric? So imagine I have totally n number of balls, capital N number of balls, of which I have m black and n minus m white balls. From this, I am choosing small n. That is, I'm randomly selecting n items without replacement from capital N, m of which are black and n minus m of which are white. So here I know that if I'm choosing small n from this, I'll have x which are black and n minus x which are white. Is this clear? Right? I'm having x is that I'm counting the number of items of black balls in this sample. Okay. So what, if I'm choosing from here, how many ways can I choose n from n? How many ways can I choose these n balls from n? Total number of ways of forming this small n balls. How many ways can I do that? I have n, which is say 500. I'm choosing 50 from that. How many ways can I choose 50 from 500?
LCM chosen.
Capital N chosen, right? Of this,
Yes.
I want to know what I can have. I want to know what is the probability of me having X black balls. Okay. Now the probability of X black balls is how many black balls did I have here?
M.
M. Out of that, I want to know what is the chance of me having X. What would that be? M choose X. Is that clear? And what is the chance of having n minus x from n minus m? It would be n minus m choose n minus x. So this is what is called the probability mass function of a hypergeometric distribution. Now I am going to tell this. I have 7 balls, of which 4 are white and 3 are black. So what is my capital N? 7. What is my M? It is 4. And my n minus m is 3. Till here, is it clear? I am choosing a random sample of 2 balls. What is my small n?
2.
2. Okay. Now, what are the values? I'm counting the number of black balls in this. So I have, suppose here, go back here. I have 7 balls, of which I had, so in this 7 balls, I had 4 of one kind, which is white, and 3 of the other kind, which is black. I'm choosing 2 balls. Okay, ball 1 and ball 2 with replacement. Is this clear? Yeah. I'm counting the number of black balls. Is it okay? Right. So what would I have? So I could have a black ball in my first, a black ball in my second, black ball in my first, a white ball in my second, a white ball in my first, a black ball in my second, a white ball in my first, and white ball in the second. Now this is, I'm counting the number of black balls. So how many black balls do I have if I come down this way? White ball in a first and white ball in a second. How many black balls will I have? In these 2 things?
0.
0. Here, in this, how many black balls will I have? White ball in the first and black ball in the second.
2.
1, right?
1.
Here,
2.
black ball in the first, white ball in the second. It is again 1. This is 2. Would you all agree? So what are the values this X is taking? X is taking the value 0, 1, or 2. So here I have both white ball in the first and white ball in the second. This is my W1, W2. This is W1, B2. This is B1, W2. This is B1, B2. This corresponds to X is equal to 2.
Tell me, call the gate.
Hello? This is X equal to 1. This is X equal to 1. This is X equal to 0. Till here, is it clear?
Yes, ma'am.
Yes, ma'am.
Okay, so you can see that for this, I have x equal to 0, x equal to 1, x equal to 2, and I can apply the hypergeometric probability to get what is the probability of x equal to 0. You can check x equal to 0 is 4 by 7 into 3 by 6, which is 12 by 42, which I get at 12 by 42. What will be the probability x equal to 1? This is 12 by 42. What is the probability of x equal to 1? 4 by 7 into 3 by 6. What is that? 12 by 42. And 3 by 7 into 4 by 6. Again, what is that? 12 by 42. So what would be the probability x equal to 1?
24 by 42.
24 by 42. What would this be? X equal to 2. What is probability x equal to 2?
6 by 42.
6 by 42.
So what do they add up to? 6 plus 24, 30. 30 plus 12, 42. 42 by 42. I have a probability mass function. Is this clear? You can just verify that this is exactly what we have. So this is a hypergeometric distribution. Okay. Now the last distribution which we are going to look at is, one thing is when we talk about a hypergeometric distribution, the expectation is n into m by n. The parameters are, what are the three things that define a hypergeometric? I need to know what is capital N. I need to know what is small n, and I also need to know what is small m. So these are the parameters of the distribution. The expectation of a hypergeometric is n into m by n, and the variance is what you see on your screen. Interestingly, what happens is I can write this as n into m by n. Okay, and here also I can write as n into m by n. Now this term, I can take out n and I can write it as 1 minus m by n. Would you all agree with it? N minus m, right?
Yes,
I can divide it by n. So this is what I'll get. N minus m by n is 1 minus m by n. N minus m by n, I can write as 1 minus m by n.
Yes,
And this one, I can write it as 1 minus n by n, 1 minus 1 by n. Would you all agree? Yeah?
Yes,
Now, suppose your capital N is very, very large compared to your n, small n. What would happen to this term? If your capital N is very large, what would happen to 1 by n?
it will be 0.
0.
So even if your capital N is very large comparing to this would go to 0. So what would happen to this term? If your capital N is very large,
It will tend to 0, ma'am.
it will tend to 0. This term will tend to 1, right? This would tend to 0. This would tend to 1. Would you all agree? Because it is 1 minus 0 divided by 1 minus 0. This would tend to 1.
Yes,
Agreed? Now, if you look at this term, then I have it as an n into 1 by n into 1 minus m by n, right? The variance. Now, does this, the expectation and the variance, does it resemble anything? Expectation of x is n into m by n. Variance of x is n into m by n into 1 minus m by n. Have you seen something of this kind before?
Yes, ma'am. For the Bernoulli trials,
By
m by n was p.
binomial, for the binomial distribution, we saw it as np into 1 minus p, right? Agreed? So the idea is, whenever I talk about a hypergeometric distribution, okay, you can see that expectation of a hypergeometric and a binomial is given here. If n equal to, that is, if this population n is very, very large when compared to your sample, then the hypergeometric is similar or it is about the binomial distribution. And I can demonstrate it using the graph. So here you can see the blue is the hypergeometric and the binomial, and the red is the hypergeometric. They are almost the same. Again, the blue is the binomial distribution. You have the parameters of the binomial distribution, n equal to 25. The capital N is 500. You look at this, as your n is becoming larger and larger. Okay, you see that the binomial and the hypergeometric are almost similar. Okay, so as n becomes large, the hypergeometric can be viewed as a binomial distribution. Now, the last discrete distribution that we are going to discuss is what is called the Poisson distribution. Again, remember, when we are talking about a discrete distribution, we are looking at basically counting. Whenever it involves counting, we said it is a discrete distribution. So the Poisson distribution basically counts the number of events occurring either in a fixed interval of time or in a fixed interval of space. So typically when you are given questions like number of accidents happening in an interval of time, or number of misprints in a book, or number of typos in a page. Book, page is interval of space. Number of accidents or number of arrivals in a interval of time. This is all interval of time. You can model this as a Poisson distribution. So we assume here that the events happen at a known average. This lambda, this is the average rate, that is the independently of the time since the last, this one. I say X is a Poisson random variable with parameter lambda, and the probability mass function is e to the power of minus lambda, lambda to the power of x by x factorial. Note, X takes value 0, 1, 2, up to something. So here I'm not telling that X will take finite number of values. When we're talking about binomial and the hypergeometric, they were taking finite number of values. It is taking discrete countably, but they are countably infinite. Okay. For a Poisson random variable, it can be shown that the expectation and the variance are the same as the parameter lambda. So I'm going to now look at some examples. I want you all to have your paper and book ready. So now we are going to test concepts. Please have your paper and book ready. I have an e-commerce company that sells women apparel. It is observed that 10% of their customers return the item purchased by them for many reasons. On a particular day, 20 customers purchased items from the company. Okay. Now, first of all, what is the random experiment here? I am interested in knowing the probability of customers returning their item. Okay. So, first of all, what is the Bernoulli trial here? What are the two outcomes of this experiment?
Returned, not returned.
Return or not return. Very good. What is the probability of which return happens?
0.1.
0.1.
So what is the probability with which return does not happen?
0.9.
And 9.
0.9.
Okay, right. So the probability with which the first customer returns, is it independent of the probability with which the second customer returns?
Yes, ma'am. It is independent.
Yes, ma'am.
So
Yes,
it is
ma'am.
independent. Is it identical? The probability with which the first customer returns, is it identical? Is it the same 0.1, or is the probability with which the second customer returns is going to be different?
It is the same.
Same.
It is the same. So can I think of these 20 customers who have purchased an item on a particular day to form a set of 20 identical and independently distributed Bernoulli trials with probability of return to be 0.1 for each one of them, which are independent and identical? Would you all agree with me? Yes?
Yes,
So I
ma'am.
have, if X is the number of customers who returned, right? What is the probability? X is a binomial with probability 20 and P, which is 0.1. Till here, is it clear? So given a problem, the first step is to, first of all, verify the IID condition. If it is verified, then identify what is N and what is P. What is small n here?
20.
20. What is P?
0.1.
0.5.
0.1.
Okay. Now, what is the first question? Probability X is exactly equal to 5. So what would this be? It would be 20. What is probability X equal to I?
20 choose 5.
It is 20. N choose I. P to the I. 1 minus P to the N minus I. This is what it is. So it would be 20 choose 5. 0.1 to the power of 5. 0.9 to the power of 15. Is that clear?
Yeah.
Right? Probability that a maximum of 5 customers would return the item. What would that be equal to? What would I want
Less
this?
than 5 plus
Probability X is less than or equal to 5. More than 5 customers?
1 minus more than.
1
This would
minus
be
X.
probability X is greater than 5. Average number of customers who are likely to return the items?
NP. Come to the expectation value.
Expectation of X, which is N into
Expectation.
P. What is N into P here?
2.
2. So on an
2.
average, how many customers are likely to return the item?
2.
2. What is the variance? It is NP into 1 minus P. So it would be 2 into 0.9. It is 1.8. Is that clear? So you can see that the probability of exactly 5 customers, you can verify these things, but this is how you can get it. Till here, is it clear? So this is a condition where we have modeled it as a binomial random variable. Now I'll go to example 2. On an average, 20 customers per day cancel their order. Okay. So what am I talking about when I tell 20 customers per day? See, the earlier thing was on a particular day, 20 customers purchased item. Out of these 20, I wanted to know how many would return. Now I'm telling you on a particular day, 20. So what is the cancellation rate per day?
1 by 20.
It is 20, right? 20 customers per day cancel their, that is the, how many customers per day cancel their orders?
Depends on number
20.
of customers.
It is, no, 20 per day, it is given to you, 20 per day. On an average cancel. So what is the?
NP equal to 20.
No, this is per day, the number of customers in an interval of time. What is the distribution that you model it as?
Poisson
That's what I want you all to get at. The same problem, but posed differently, right? So what is this X?
Lambda.
X is a Poisson. What is your lambda? It is
20.
lambda equal to 20. Is this clear?
Yes,
Yeah.
ma'am.
Yes,
Right?
ma'am.
Now, once I identify this, I can find out what is probability X equal to 20. Right? What would that be? E to the power of minus lambda, lambda to the power of 20 divided by 20 factorial, which is about 0.0888. You can verify that. So what is the probability that the maximum number of cancellations will be 25? I'm looking at probability X is less than or equal to 25, which will be a cumulative probability. Till here, is it clear?
Yes, ma'am.
Yeah. Okay.
Yes,
Let's
ma'am.
test the third problem. In a batch of 10 spare parts, there are 3 defective. Okay. 4 of these parts are selected at random. X is the number of working spare parts. First of all, what is this distribution here?
Hypergeometric.
So from 10, I have 4 which are defective, 6 which are non-defective. How many am I selecting? 4. Okay. So what would be the value this X would take?
Ma'am,
The defective parts is
3 are defective, ma'am.
Pardon?
3 are defective, ma'am.
Yeah, 3 are defective. Oh, sorry, 3 are defective. How many are non? This one, 7, right? 3 defective, 7 working, right? I'm looking at 4. So what are the number of working parts?
0, 1, 2, 3.
If it is 0, then how many defects? So just think about it. I'm selecting 4 parts at random.
So 0 is not possible.
And 0 is not possible. 1, 2,
That's
3
what
and
I want you all to see, right? Is that clear? So what are the, so I can have out of these 4, can I have all 4 of them working?
Yes.
Yes.
Can I
Yes,
have
ma'am.
all 3 of them working and 1 defective?
Yes.
Yes, ma'am.
2
Yes, ma'am.
working, 2 defective?
Yes, ma'am.
Yes,
Yes.
ma'am.
1 working, 3 defective?
Yes,
Yes,
ma'am.
ma'am.
Yes.
None working?
No, ma'am.
No,
I
ma'am.
cannot have this. So what are the values this is taking? 1, 2, 3, and 4. Is that clear?
Yes, ma'am.
Yes, ma'am.
And now you can get the probability mass function. What would be the denominator? It would be 10 choose 4. Numerator for this would be 7 choose 1 into 3 choose 7 choose 3. Sorry, 1 is working. 7 choose 1 into 3 choose 3. Plus for this I have 2, 2, right? 7 choose 2, 3 choose 2. This would be 7 choose 3, this one. Sorry, this 7 choose 1. This is 7 choose 1, 3 choose 3, 7 choose 2, 3 choose 2, 7 choose 3, 3 choose 1, 7 choose 4. So that would be my probability mass function. You can get the cumulative distribution function. I would leave it as a, what is your small m? What is your capital N here? It is 10. Small m equal to 7. I will leave it as a this one for you all to check what was the expected value and the variance. Okay. So with this, we finish the discrete random variables where we started with the Bernoulli random variable. Then we went on and looked at the discrete uniform distribution. Then we defined what was the binomial distribution, where we introduced the notion of IID, which is independent and identically distributed. Then we introduced hypergeometric, where I lose the IID, and finally the Poisson distribution. Any questions here?
Yeah, ma'am.
Yeah.
Could you,
Yeah, please go ahead.
in example 1, could you explain me the part 4, that average one?
Which one? Average number of
The
customers.
average number of customers
Yeah.
who are likely to
What
return
is
back.
X here? What is X? How are you defining X here?
X is the number of people who are returning the items.
Out of these 20, number of people who are returning, right? And what are
Yeah,
you asking? And what is the distribution of this X? It is a binomial random variable.
it is a, yeah,
What is N here? Small n,
small n
20?
is 5.
20,
Yeah,
right?
sorry.
Okay.
Yeah,
Now, I want to know what is the average or the expected number of customers who are likely to return. So I want to know what is the expected number of customers who are returning. If I
right.
have a binomial random variable with parameter n and p, what is the expectation of x?
N.
N into P,
N into p. What is n here in this example?
20.1.
20.
What is p? 0.1.
0.1.
So
Okay.
on an average, how many people are you expecting to return?
2.
2.
2. That is what I have. Is it
Okay,
clear?
okay, got it. Yeah, yeah,
Got it?
got it.
Yeah.
Yeah,
So here I've given you the average. So suppose I ask here on an average, how many customers do you expect to cancel? That is given in the problem.
yeah, it
Which
is.
is lambda, right? In a Poisson,
Yeah,
that is lambda. What is the variance of this random variable?
Lambda.
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 That is also 20, right? Is it clear?
Yeah,
Yeah.
yes.
Here, this was a hypergeometric. So we learned 3 key things, which is binomial, the hypergeometric, the Poisson, and the hypergeometric. Is that clear? Is this clear now? Any more questions?
No, ma'am.
Okay, right. So now we move on to continuous distribution. As I said, when you're talking about a discrete distribution, you are involving counting. So if you're looking at it, you're looking at number of successes in n tosses, number of defectives, number of accidents, number of typos. This is where you are involving some counting. Okay. On the other hand, when I talk about a continuous random variable, I am talking about probability of this random variable belonging to an interval. I'm not asking what is the probability X is taking a value. I repeat, when I talk about a continuous random variable, I'm asking about probability X is belonging to an interval as against probability X is taking a particular value. Is this clear, this distinction?
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
when by convention, the probability that X belongs to an interval. So if X is a continuous random variable, the probability X takes a value is assumed to be 0 because it always belongs to an interval. Okay. Now the simplest of the continuous random variable is what we refer to as a uniform distribution. Just as I had a discrete uniform distribution, I have a continuous uniform distribution where I have A and B. Now, the analogous, I talked about probability X equal to I don't have probability X equal to I here. Rather, I have what is called the probability density function, which is giving me what is that? It is a curve. It is telling me what is the probability of me finding a random variable in an interval. So if I have X here, the value X is between A and B. If X is a uniform distribution between A and B, then I have uniform density. So I could have a density which is like this. I could have a density which is like this. All I need is if it is a density function, the area under the curve should be 1. Why is this so? Because I know probability X equal to Xi was equal to 1. The analogous area, you all know that this, when I have this, I'm adding up different probabilities. This, when I have multiple such thing, it is going to be the area under the curve. So I want the area under the curve to be equal to 1. Okay, probability X equal to Xi is the same as the area under the curve is equal to 1. So now when I'm talking of a uniformly distributed random variable, what I have is I have a, I have a B, I have my density here. Okay, this density is uniform between A and B. So what is the area under this curve? This is B, this is A. What should this area be?
1.
1.
B minus
Now,
A.
if this is A and this is B, what is this length?
B minus A.
B
B
minus A.
minus A. What is the area of this? Suppose this is constant. What is the area of this?
B minus A into K.
Constant.
And what should this be equal to?
1.
So what is the value of K?
1 by B minus A.
So I have the density of a uniform distribution, which is 1 by B minus A. For A is less than or equal to X is less than or equal to B. I can write it as A is strictly less than X is less than B because X equal to A doesn't mean anything and 0 otherwise. This is what I refer to as a continuous uniform distribution. Is this clear? I can verify what is A to B 1 by B minus A dx. This is equal to 1, right?
Yes.
Agreed? Yeah. So it is a density function. Now, just as expectation of X was summation over X into probability X equal to X or Xi into I over all I, the expectation of X here is going to be X into f of X dx. The same thing, X, P of X replaced by f of X. So what is the expectation of a uniform random variable? It would be A to B, x into 1 by b minus a dx. What would this be? 1 by b minus a, I can remove a to b x dx. So what is this? What is the integral?
X square by
X
2.
square by 2.
Square by 2.
X square by 2, but from b to a, what would I get? I'd get a b square
Square
minus
minus a
square
square
by
Minus
by
a
2
square
into
by
b minus a.
B
What would
plus
this be?
A plus B by 2.
A plus b by 2. So you can see that the expectation of a uniform random variable is nothing but a plus b by 2. Is this clear? And you can verify that the variance is b minus a whole square by 12. Now, what is a cumulative distribution function? Now, you can know that if I look at a uniform distribution, I know that this is the PDF. I have a here, I have a B here. If A is less than B, I know this is 1 by B minus A. So what is f of x for any value which is less than A? What is the value here? So if I'm going
0.
to plot f of x, it is going to be 0 till it is A. At A, what is the value? It is 1 by B minus A. It is going to remain 1 by B minus A till it hits B. At B, what will it be? It would be B minus A by B minus A. This is what is going to happen. So what I'm telling is for any x between A to B, what is f of x? I'm interested in knowing what is this value, right? X is between A to B. So this would be 1 by B minus A. Agreed? F of x is 1 by B minus A. What is A to x dx? That is nothing but x minus A by B minus A. Would you all agree with it? A to x dx is nothing but x minus A, right?
Yes, ma'am.
Right? But if you look at this x minus A by B minus A, I can write that x by 1 minus B minus A by B minus A, which is minus A by B minus A plus 1 by B minus A into x. Now, what does this resemble? The equation? A and B are constants.
Straight line
A
equation.
It's a straight line equation. So you can see that the cumulative distribution function is a straight line between A and B. And then in a discrete, what did I have? I had discontinuities. Here I don't have discontinuities. This is how the cumulative distribution function of a uniform distribution appears. Is this clear? Yeah. The next thing is application of a uniform distribution. You are to meet a friend at 2 p.m. However, when you always arrive exactly on time, your friend is always late and will arrive in the place at a time which is uniformly distributed between 2 and 3 p.m. So if X is the amount of time you're waiting, what is the amount it is uniformly distributed as? How much? I'm measuring the time you're waiting. So what would be the amount of time you're going to wait?
2 to 3.
2 to 3
From
p.m.
2
But
to 3 p.m.
60 minutes.
1 hour, ma'am.
6
1 hour.
0 to
60
60
minutes.
minutes.
60.
Right? In terms of minutes, it's 0 to 60 minutes. Is that right? So if it is 0
Yes,
to
ma'am.
60 minutes, what is your f of x? 1 by 60. For 0 is less than x is less than or equal to 60. Would you all agree?
Yes, ma'am.
And what is probability x is greater or equal to 30? So I have 0.
Why
60
is
with
it? Why is it like 1 by 60 less than equal to x and less than equal to 60? No, is it not 1?
It's 0, right? You at a time, see if you are meeting,
1 by 60 minus 0.
if friend comes at 2 o'clock, how long are you waiting?
0.
0.
If it's coming at 3 o'clock, how long are you waiting?
60
60
minutes.
minutes.
But this is uniformly distributed. That is you are
No,
waiting
ma'am.
for
Ma'am,
any
that is not
time.
my question, ma'am. The f of x equal to 1 by 60 less than equal to x less than equal to 60 you gave, no, ma'am.
Yeah, 0 is less than x is less than 60.
Oh, is it 0? Okay.
Yeah, this is 0.
Oh, okay, ma'am.
Okay. What is probability x is greater than 30? It would be this
1 by
area.
2.
What would it be? Just
30 by 60.
it is just The total area is going to be 1. What is the probability x is greater than 30?
Half.
1 minus.
Half. Less than 15? So this is all very
Quarter.
simple, right?
1/4.
Between
1 by
10
4.
and 15, you can see that you can just keep adding. Less than 15 is 1 by 4. Greater than 30 is 1 by 2. Less than 45 is 3 by 4. Is this clear?
Yes.
Yes, ma'am.
So this is just application. So what did you do here? The first thing is you need to recognize that hello. The first thing you need to recognize is I have a random variable, which is continuous random variable, because I'm looking at measuring the time. I'm not counting the time I'm going to wait, right? I'm asking how long are you going to wait? When I'm talking about how long you're going to wait, are you counting or are you measuring? Measuring. So I'm measuring the time between 0 and 60 minutes, and I'm recognizing that is a uniform distribution. I'm recognizing what is the PDF, and I'm answering the questions. Is this clear?
Yes, ma'am.
Right?
Ma'am, there is some similarity between Poisson distribution and this distribution.
Not really. No. Because in Poisson, you're counting, right? The number of events happening in an interval of time. Here you're asking what is the distribution of time. Poisson is a discrete distribution.
Okay.
Is that clear?
Yeah.
Whereas here you're asking what is the chance that I'm going to wait for more than 30 minutes. I'm not counting anything here. I'm measuring how long I'm going to wait. I'm not counting. Is that clear? If I had asked the number of hours you're waiting, then in that case, in a day, how many hours you're waiting, that is a count again. Is that clear?
Yes, ma'am.
Okay.
We can count it as how many minutes we will wait, like that. Can you do
If
it?
you're counting number of minutes, but usually you don't count the number of minutes, right? You're just asking how long you're waiting, right?
Yeah, we don't.
Right, that is how you're asking.
Yeah.
So that is why you're just going to tell whether it's greater than 30. It is a continuous random variable. I'm not asking. So here, if I ask a question, what is the probability that you're going to wait exactly 30 minutes? What would be the answer? X is equal to 30. For a continuous random variable, what is probability x equal to I?
0.
0, right? So that's how you want to answer. Is that clear? Is that clear?
Yes.
Ma'am, but
Yeah.
in practicality, that is possible, no? Like I can wait for like exactly 30 minutes.
Yes. But when you're assuming it's a continuous distribution and you're modeling it as a uniformity or less than or equal to 30, that probability x equal to I, you're assuming it to be 0 because x is always belonging to an interval. It is not taking a discrete value.
Okay, ma'am.
Is that clear? Yeah. I'm just going to skip this. This is there in the notes. I'm going to go to the next problem, which is an exponential distribution. Now, why is exponential distribution very important? You see, many a time when we are modeling time in what are called queuing systems, right? When I have a queuing system, what do I have? I have people, for example, arriving at a particular bank. There are two types of time distribution. One is the inter-arrival time between people. That is, person one comes, person two comes. There is a inter-arrival time between person one and person two. There's an inter-arrival time between person two and person three, right? And are they always the same, or do you expect some answer distribution in that? Suppose I have 20 people arriving at a bank in a particular day. There is a number of people arriving at a bank in a particular day. What distribution would it take? Number of people arriving in a bank between 9 and 12.
Poisson distribution.
Poisson distribution. But that is not what I'm talking about here. I'm talking about the distribution of time between the arrival of two people. Now, will it be a continuous distribution or will it be a discrete distribution? Time between two people. That would be continuous. Is that distinction clear? When I talk about number of people arriving at a bank between 9 a.m. and 12 a.m., I'm asking about the number of incidents in an interval of time. But I'm talking about the distribution of time between two arrivals. This is called inter-arrival time. Similarly, for the person who's serving the customer, the teller, okay, the person who's serving the customer, that will also have it is the amount of time a person is taken to serve a customer. Will that be same or will that be different?
Different.
Different. So these distributions typically both on the inter-arrival time and the service times are mainly modeled based on what we call exponential distribution. Now, in advanced courses, you will learn that this exponential distribution has something called the memoryless property. But what is an exponential distribution? A random variable which has the probability density function as what you see on the screen, which is lambda e to the power of minus lambda x. If x is non-negative, 0 otherwise is said to follow an exponential distribution. The parameter of the distribution is said to be lambda. So you can look at the graph of the PDF for different values of lambda. So lambda equal to 0.5, you see is the black, the blue, the red is for lambda equal to 1, lambda equal to 2 is 0.2, and the cumulative distribution function, which is because I know lambda e to the power of minus lambda x, again, if I am going to take lambda outside, I know the integral of 0 to a e to the power of minus lambda x is e to the power of minus lambda x into minus. So I get 1 minus e to the power of minus a, which is my cumulative distribution function. And you can see that this is the graph. For the uniform, it was a straight line. Here it is 1 minus e to the power of minus lambda a. So you can say that after a particular point, everything tapers to be 1 because it will lie between only 0 and 1. This is the shape of the curve for different values of lambda. The expected value of a exponential distribution is 1 by lambda. The variance is 1 by lambda square. You can verify this through integration by parts because the expectation of e to the power of xn is this. Again, this comes from integration of parts. If I want expectation of x, it is 1 by lambda into expectation of x to the power of 0, which I get it as 1 by lambda. Expectation of x square is 2 by lambda. Expectation of x, which is 2 by lambda into 1 by lambda, which is 2 by lambda square. So what is my variance of x? It is 2 by lambda square minus 1 by lambda whole square, which is 1 by lambda square, which will give my expectation of x is 1 by lambda and variance of x is 1 by lambda square. So let's look at what is an example. So suppose the length of a phone call in minutes is an exponential random variable with parameter 1 by lambda, with parameter lambda. If someone arrives immediately ahead of you at a public telephone booth, find the probability that you'll have to wait for more than 10 minutes. What is it I want to know? Probability x is greater or equal to 10, right? What is probability x is greater or equal to 10? 1 minus probability x is less than or equal to 10. Would you all agree with me? Now, this is the cumulative distribution function, f of 10. But what is f of a? 1 minus e to the power of minus lambda a. Agreed? So, this is 1 minus e to the power of minus lambda into a, where it is 10 lambda, which is e to the power of minus 10 lambda. What is lambda here? What is the value of lambda?
0.1.
What is minus 10 lambda?
1.
So it will be e to the power of minus 1, which is approximately 0.368. So the probability that you will have to wait for more than 10 minutes is e to the power of minus 10. What is the probability that you will have to wait between 10 and 20 minutes? It's probability 10 is less than x is less than 20. What is, I know probability x 10 is less than or equal to x is less than 20 is the same as f of 20 minus f of 10. Would you all agree with it?
Yes,
Probability x is less than, yeah. But what is f of 20? That would be 1 minus e to the power of minus 20 lambda minus 1 minus e to the power of minus 10 lambda, which is e to the power of minus 1 minus e to the power of minus 2, which is about 0.233. Is this clear? Yeah. So the chance that you'll wait for more than 10 minutes is about 0.37, 37% chance, and you'll wait between 10 and 20 minutes is about 0.233. Here you're recognizing that it's an exponential random variable, and you're actually applying the cumulative distribution function, which is f of a is 1 minus e to the power of minus lambda a, knowing what is your lambda. Okay. Now with that, I complete this revision. So what we did today was we started with reviewing the definition of a random variable. Mainly, we looked at what was the discrete probability mass function for a discrete random variable, the cumulative distribution function, what is the expectation and variance. We looked in particular what is a Bernoulli random variable. Then we looked at discrete uniform random variable. We talked about what is independent and identically distributed random variable. Then when I did not have the independent and identically distribution, I went and introduced what was hypergeometric, then looked at Poisson distribution. Then we introduced what was the uniform distribution. And the key thing that we wanted to know is, given a problem, we need to understand what is the parameters of the uniform distribution. It could be between A and B, recognizing A and B from the problem. In the example that we considered, A was 0, B was 60 minutes, and then we applied the problem. We looked at exponential distribution, in particular, what is the cumulative distribution function that given the parameter, I know that it is 1 minus e to the power minus a into lambda. We applied that in an application to know if x is an exponential with a given parameter, how do I compute the value of waiting for more than 10 minutes or waiting for between 10 and 20 minutes. Okay. Thank you all. I have 4 more minutes. If there are any questions, I would be happy to answer.
Ma'am, normal distribution is a part of syllabus?
Prashant, can you answer that, please?
Yeah. So normal distribution is not the part of syllabus this term. So only till exponential distribution will be there.
Okay.
Yeah.
Ma'am, I would like to understand what variance exactly tells. Like if we take a
yeah. Yes, good question. See, what variance exactly tells us? See, many a time, let me start from without even going to probability, right? Okay. Let me tell you that now, because it is IPL, suppose I have a batsman who is scoring consistently 15, 15, 15, 15, 15, or 30, 30, 30, 30, 30 in 5 matches. What is the average he's scoring?
Same. Like
30, right?
30.
But there's another batsman who's scoring 10, 20, 30, 40, 50. What is the average?
A bit different.
30.
It will also be 30, right? But who is the more consistent of these two people? Both of them have the same averages.
First one, ma'am.
Who is more consistent? If I were to ask you what is the consistency, who is the more consistent player?
The first one.
The first one, ma'am.
First one. Yeah.
Right. So how did you tell that the first one is a consistent player? Average. So if you're looking at a numerical metric, both of them have the same averages. So it needs a metric which is able to tell this variation, right? The first one has absolutely no variability, but the second one has a variability. Would you agree?
Yes, ma'am.
That is what the role of variance. Variance is a measure of dispersion, whereas average is a measure of central tendency. Okay. So whenever I have variability, in addition to my numerical measure, see, whenever I have data which is spread over, I have where is the data expected to be concentrated. That is a measure of central tendency, and what is a measure of dispersion. Variance is a measure of dispersion. Now, when I'm looking at this was a more discrete or it was a deterministic sample. When I look at random variable, the notion of average is what I am capturing as in the long run, what is the expected value? That is what expectation does, and the similar role of dispersion is played by variance. Did I answer your question?
Yes, ma'am. Thank you very much.
Yeah. Right.
Ma'am, I have one more question.
Yeah.
Yeah, for a continuous random variable, any distribution it follows, uniform or exponential, can we find the probability at any particular sequence or any particular?
See, that's what I said. See, whenever you're talking about a continuous random variable, you're telling x belongs to an interval rather than telling x is taking a discrete value.
Okay.
Okay. So the probability x takes a discrete value is taken to be 0. We are always talking about x belonging to an interval, however small that interval is. And that is how we are defining that probability x belonging to a interval.
If at all a question is framed like we have to find the probability at a discrete value, will it be 0? Should we assume it to be 0?
It will be 0, yeah.
Yeah, okay.
For a continuous random variable, yes.
Okay.
Okay, yeah.
Ma'am,
Yeah.
how I can identify which questions I solve by exponential distribution or from continuous distribution?
See,
It's
it would be typically mentioned. For example, if you look at the examples, we said that your friend is expected to arrive anytime between 0 to 2 and 3 p.m. with equal probability, right? So what would that be? It would be a uniform distribution. Agreed? Yes. On the other hand, in the second example, I said that this time is assumed to be exponentially distributed.
So it will be always said we have to assume
Most of the time it is given. Most of the time it is given. You see, it depends on the question. So typically, exponential distribution is a way to model inter-arrival time, service times, time taken from A to B, and all of that. So it would be given. Yeah.
Okay, thank you.
Yeah.
Madam, I have one question,
Yes,
but
please.
it's not from lessons. If you allow me, I can ask. So it is related to the statistics only. See, I'm from the working person. So we have in industry Six Sigma and all. So I have doubt this statistics 1 and 2 if you covered. So it will be enough for the Six Sigma concepts.
See, to understand Six Sigma, there are two things that you need to do. One is you need to understand what is normal distribution.
Okay.
Okay. That is from the statistical aspect of it. The second thing is Six Sigma is what we refer to as a process capability index. Okay. So that is why you need to understand what is the voice of the customer and the theory behind that, and you will be able to fit in. If you understand what is normal distribution, you'll understand the math behind Six Sigma. To understand the philosophy behind Six Sigma, you need to know what is the capability of the process, what is the control of the process, and what is the process capability, what is voice of the customer, and all of that. That comes from quality management.
Okay. Okay. Thank you, madam. Thank you.
Can you explain triangular distribution once more, like the summary of it?
See, triangular distribution is not anything very different. It is just that, let me show you the. So are you able to see my screen?
Yeah.
Yeah. See, in this, I have just plotted this triangular distribution. See, it is, as you see that if I have to describe the density function, it is going to take a value between 0 and 2, and it will take another value between 2 and 4. Would you agree with it? So if I have, it is a straight line between 0 and 2, it will have a negative slope between 2 and 4. So the density function is first what I want to describe. Okay?
Okay, ma'am.
It would be different. So I need to know. So if it is between 0 and 2, f of x is going to be this line. Between 2 and 4, it would be a different line. But here, because I have given the grid, in this example, it was very simple that between 2 and 4 p.m., that is, I know between 4 hours, this is the distribution. I've just asked you now, what is the height of this curve at value 2? You can easily find out that what is the area of this triangle.
Okay, ma'am. So there's
It
no
is 1.
formula, is it?
That's it. The area of the triangle is 1, and that's how we are finding it out. But I have not
Okay.
given you what is the PDF of a triangular distribution, because that is not what we were expected to know. This is just a very specific example of a triangular distribution, not a
Okay.
general.
So there's no
formula.
formula, right? Just
There
equal
is,
to
but
1.
that is not what we have covered in the syllabus. In the
Okay.
syllabus, from the syllabus perspective, only the uniform and the uniform
Okay.
exponential is what is. This was just a very specific example.
Yeah, okay. Thank you, ma'am.
Okay.
Ma'am, in Poisson distribution,
Hmm.
and it is a discrete, but it is used for time.
Hmm.
Can you explain why?
Pardon. Can you repeat the question?
In the Poisson distribution is for the discrete one, right? Then why is it used to calculate time?
It is not used to calculate time. It is used to compute the number of incidents in the given interval of time. There's a very big difference. Number
Okay,
of accidents that happen between 9 a.m. and 11 p.m. It is not asking you to compute the time. It is counting something in a given interval of time.
Okay, thank you, ma'am.
Okay. Okay, I think I'll stop here. There is one comment which asks me to teach in Hindi. I think I can speak Hindi, but I don't think I have fluency in that language to teach in that language. I think Prashant and Nikita, you are already having a Hindi version of it, right? If I understand right, Prashant?
Yes, ma'am. Yes, ma'am. We
Yeah,
have
so
already there
yeah,
on the
there are people
portal.
who are much more fluent in Hindi. मैं बात कर सकती हूँ पर उतना fluent नहीं है. So I don't think I would want to teach in that and make mistakes. Okay? Right. Thank you all. Wish you all the best. I think there
Thank
are
you,
no more
ma'am.
questions. Thank you all. Yeah.
Thank you,
Thank
ma'am.
you.
Riddhi also good.
Ma'am.
It was nice meeting you, ma'am.
Good night. Thank you.
Thank you, ma'am.
Thank you for session, ma'am.
Thank you. Thank you.
It was nice meeting you, ma'am. Thank you so much.
Thank you. Thank you all. Wish you all the best. Yeah.
Ratri, ma'am.
Thank you.
Thank you.
Thank you, ma'am.
Portion for the end term will be 8 to 12, right? Does anyone know about it?
What are you asking?
I wanted to know the end term portion. Will it be from 8 to 12 weeks?
No, from 1 to 12.
1 to 12, okay.
But it
The
will
major
include
portion
majority of
covers it
8 to
to
12.
12. 8 or 9 to 12.
Majority portion will be from 8 to 12 weeks.
Yeah, these are the new topics, right? So,
Yeah, major from 8 to 12, but it will cover 1 to 12.
okay.